Hi, my name is George. Sorry for not being able to attend the conference. I hope you are enjoying it. I will talk about the paper I've co-authored with Renato Keshet and Alina Moore from the Hewlett-Packard Enterprise Lab. The paper title is Prediction-Based Prioritized Market Share Insight Extraction. The talk will go as follows. First, I will give a short background. Then I will describe the gap and define the problem. I will describe our approach in a high level. Then I will show you our testing methodology and some results. Business intelligence, or BI, is about providing decision makers with the critical information for running their businesses. It is a set of processes and technologies that are used to support the collection and analysis of business information. The earliest known use of the term business intelligence goes back to 1865 by Richard Miller. Richard used the term to describe how the banker Sir Henry gained profit by receiving information about his environment prior to his competitors and acting according to this information. In general, the goal of BI is first, easy interpretation of business data, allowing businesses to identify new opportunities, implementing strategies, and providing businesses with competitive market advantage and long-term stability. Traditional BI systems usually provide reports which list summaries and business insights. Also, they provide dashboards which show aggregated indicators about the business health. These summaries and aggregations are key for decision making. The problem is that there are often hundreds or thousands of ways one can aggregate data to look for insights indicators. For instance, if a sales table contains columns such as product, country, region, and category, then one could aggregate product by countries or categories by regions or regions by product and categories, or combinations are possible. Here we refer to each such aggregation as a player in market. For example, if one looks at the aggregation of the product P2 in Canada, we call P2 the player and Canada the market. Notice that Canada could also be player in the P2 market. This approach is known as online analytic processing, or OLAP. It is semi-manual in the sense that the aggregations are done automatically by the OLAP engine, but the choice of players and markets are made by the analysts. BI vendors usually provide the various ranges of dashboarding, reporting, and OLAP capabilities. What analysts usually do is to analyze players in a pre-selected small number of markets. Each widget in the dashboard is a graph of the performances of players in a particular market. The pre-selected players and markets are typically high level. At each point in time, the user visually inspects one or few markets, and if they see something interesting, strange, or anomalous, they dig down into it to more specific markets until they discover the root cause. One of the difficulties with the traditional OLAP is that it's semi-manual. Analysts need to manually explore the different markets by actively slicing and dicing, and thus navigating the maze of markets and the submarkets. This manual process sometimes leads to analysts missing critical insights, because key events may be diluted or cancelled out when aggregated. Such events fly under the radar, which usually leads to inaccurate decisions. What we propose is an approach and a computer system for mining market share data. Our analysis engine performs automatically all possible slicing and dicing of the OLAP cube. The system is nevertheless interactive, enabling the user to choose the attribute for analysis, tuning the relevant weights and markets and players. The main challenge is in computing the significance score for each player in each market. The significance score can be used to return relevant insights to the analyst. Differently from previous solution, our solution analyzes players' shares rather than values in each market and perform the analysis based on time series predictors. The use of market shares is advantage because first, it is often what iterates the analyst, and second, it neutralizes player oscillation in oscillating markets. The time series analysis enables us to provide the user with significantly unpredicted changes. Here we see a snapshot taken from the proposed market share analytics tool applied to the IDC WW server tracker data, which we will discuss later. It checks all market events in all existing markets, detects the most significant market share changes, prioritizes them, groups related insights together, and returns the corresponding visual graphs. At the upper left, the user chooses the period to consider, and the list in the center displays the top insight for that period. Upon clicking on an insight, related events are displayed. We think of each insight as a headline in a news outlet, and the related events convey the story. To the right, graphical information related to the story is provided. To the bottom left, the user can interact with the results by choosing attributes and setting filters. To the top, the user can create categories of interest. So how does it work? Consider a table of cells. It shows a deal, and each column is an attribute associated to that deal. Suppose at least one of those attributes is a time period where the deal occurred, for example, week, month, quarter, and at least one additional attribute is the deal value, which is used to measure the market share, for example, revenue, number of units, etc. Let us denote VTM as the volume of the market M at time t, and ZTPM as the market share of player P in market M at time t. As we have mentioned before, our engine is based on calculating the significance score for every player in every market to give a prioritized list of insights. The significance score is a multiplication of three factors: the surprise factor, the relevance factor, and the user-defined weights. We do the calculation for every possible market M, every possible player P, and at every time t, where STPM is a surprise factor. This indicates how much the engine is surprised by the occurrence of market share ZTPM, given all the knowledge it has about previous values of the player's share in that market and other players in that market. For instance, if for a given player in the market, the share value at time t is significantly different from its shares in previous times, then the surprise value will be high. The other factor is RT, which we call the relevance factor. This factor represents the relevance of the player or market to a particular use case. In our implementation, we set the market volume as a relevance factor, so that the bigger the market, the more we are interested in it. WPM is a user-defined weight. The engine supports user feedback either by directly setting weight for a particular player in a particular market or providing hints such as like and dislike. This transformed into a specific weight. To calculate the surprise factor, we use a time series predictor that takes some context from the past of the given market share and predicts the value of the next sample. Let D represent the past data context data. Let capital Pi be the predictor, and let Z be the random variable representing the market share of the player. Let small pi be the prediction of market share Z given the past data D. And Fz given pi is a distribution of Z given a particular prediction value pi. We assume that the Fz pi has the following format. We assume that capital F pi is a convex parametric function with minimum at Z equals to pi, the prediction pi, and C is a normalization constant. We will refer to big F pi as a surprise function. We denote the surprise value using rho, and what eventually we get is that the surprise value can be represented as a subtraction of f of Z minus f of pi. In order to establish the surprise factor, what is needed is to first verify that the distribution of Z given pi can be approximated by C multiplied by x minus f pi Z, and second, to estimate the surprise factor f pi. For example, if the distribution of the market share Z given pi can be approximated using the normal distribution, the surprise function will equal to the factor that we see here, where mu, the mean, is pi, and sigma is the standard deviation of the distribution of Z given pi. In this case, the surprise factor equal to the Mahalanobis distance between Z and fz pi, as we can see here. In practice, since Z is a market share, it exists only inside the finite interval between 0 and 1. Thus, we do not expect distribution of Z given the prediction pi to be normal. Let us consider the input data as if it's coming from a financial nature. One typical way of modeling financial data is by means of multiplicative model. For instance, demand is viewed as a product of a deterministic and random variables, where the random variable is uncertainty quantity and the deterministic variable is a prediction. Following this multiplicative assumption, let us model the volume Vp of player P given the prediction as a random variable y of the format y equals xx, where x is a normally distributed, and the random variable z represents the market share of player P in market M given the prediction value pi. In this case, z will be equals to y over y plus c. Therefore, one can express x in terms of z. As we see here, x equals to log c plus lz, where lz is the log of z over 1 minus z. The function L is the inverse logistic transform, which called logit function. This implies that if one applied the logit transform to a realization of market share predicted to be equal to pi, then the result should be approximately normally distributed, assuming the multiplicative model holds. In other words, f Lz given pi is a Gaussian distribution. As mentioned before, a normally distributed fz pi corresponds to the surprise factor rho z being the Mahalanobis distance. We validated our model using both synthetic and real-world data. In the following, we will describe the synthetic data generation process. We generated synthetic data using the multiplicative model to simulate tables of sales in a supermarket. Each row of the table relates to a transaction with the following fields: month, product, country, customer type, channel, and value. For the first month, 10,000 rows were drawn using the distribution given in the table that you can see here. All the 10,000 transactions received value equals to 1. For the second to the month before last, we copied the same 10,000 transactions from the first month, but added a multiplicative noise to the transaction value using C, where R is a random number uniformly drawn from the 0-1 interval, and N is a noise parameter. For the last month, we repeated the same procedure, but introduced a change in a particular market for a particular player. We multiplied the transaction value by a factor f from the list shown. We have targeted the following players in markets: country USA in market care, and country Mexico in market diary, and customer type infrequent. Here we display the zero-hold predictor results that was used to calculate the surprise factor. The left table is for modification number 1, and the right table is correspond to modification number 2. The numbers provided in each of the tables are the position of the first retained insight that matches the player and market value for the targeted modification. For instance, for modification 1, for noise 1.1 and factor 0.7, the algorithm returned product care in market USA as a top insight. Then we set the appropriate cell in the table to 0. If the fifth insight, then we set it to 4, and so on. For the first modification, you can see that even when the noise is very high, the confusion happened only on small modifications. For deeper modification, like as we see in table 2, the algorithm correctly detects the correct insight for not so high levels of noise and not so small modifications. Using a more advanced time series predictor called ARIMA, the results are much better. You can see much more zeros indicating that the targeted modification was identified as a first insight. The results shown in this are typical. We saw that other similar targeted modification yield similar results. As expected, you can notice that targeted modification number 2, which is in a deeper market, have less robust results. For the shallower modification, as we can see in number 1, only a very large level of noise confused the algorithm in such a way that the targeted modification is not detected as a first insight. More interesting that those with synthetic data are the experiment we did in real-life data. The main data set we worked with is the IDC WW quarterly server tracker. It consists of a table containing hundreds of thousands of server sales transactions, involving several vendors since 2003 until today. Each sale record contains several attributes. Besides of the timestamp and the revenue value, the table has fields such as vendor, region, country, product, shipment type, processor, and several other fields. Our first step was to check whether our assumption holds. That is, the data can be approximated by the multiplicative model. Due to time limitation, I will not go over this, but you can see it in the paper. Evaluating this output is harder than the synthetic case, as typically there are no ground truths for one to compare to. It is not feasible to ask an expert to sort hundreds or thousands of market share changes in order to use it as a ground truth. And even if one does that, it is likely that two experts will rank differently. Thus, the algorithm may not be wrong if it sorts it also differently. The approach we took was to correlate some of the results with real-life events. One test we performed was to check the year 2010, when Cisco entered the US market and got a significant market share. BI systems were slow to detect that trend due to the relative low volumes involved. Our tool showed that Cisco growth in the blade market in the US as one of the top insights. And when we searched for the term blade, it showed that same insight as number 1 in the list. The top insight for that year were that Oracle overall market share increasing from 0% to 6.4%, and second, that Sun Microsystems dropping from 6.3 to 0, which means that the system successfully discovered the purchase of Sun Microsystems by Oracle in that year. A similar check for the year 2014 has showed the system showed a top insight the drop for IBM in product category x86. At the same time, the system showed as insight 5 an increase for Cisco in that same category. Thus, correlates well with the fact that Cisco indeed purchased the x86 line from IBM in that year. So to summarize, we have presented a tool for analyzing market shares and returning the top insights. The tool is based on prediction of market share for all possible players in all possible sub-markets and presenting those with larger significant scores. The significance score consists of the product of surprise factor, the relevance factor, and the user-defined weights. We have built an interactive tool which enables a user to explore their data using the Insight engine. We have evaluated it in synthetic data and using real-life sale transaction data. We showed that real-life results indicated good correlation between the insight obtained and significant market events. Thank you for listening.